Welcome back to our first real episode of Math Labs. We're really excited for our topic today. It's something that we've both heard of before, but we're getting into it this semester too. Preview, I guess, if anyone is a fan of algebra or group theory or rings, you've probably heard of the Quaternions before. It's probably your favorite group or ring.
Or if you've struggled with making computer games or using rotations on like iPhones or mobile devices, you may have heard of Quaternions and may have elected not to use them.
Probably, yeah.
In favor of Euler angles. So what we're going to do today is we're going to start at the very basics of what the Quaternion group is. And then we're going to work our way up to like more practical applications and like why the Quaternion group is cool, because that's I think what interests me the most is like okay, well, so we have this like abstract concept, but now like what are we going to use it for?
Yeah, aside from just the cool name and like the group structure, how does it apply to our everyday lives and that kind of thing. So, getting started, we figured we would give you guys a quick group theory background of the Quaternions. So, it's a non-abelian group of order 8, which is really cool. There's only 2 of those.
So,
let's break that down.
Yeah, that was a lot of words right there.
Yeah, okay, so non-abelian. So, we're talking about this strictly in terms of group theory. So, non-abelian just means that the operation does not commute in order. Yeah, okay, we should back it up like 10 steps.
Okay, so
let's talk about the elements first.
Just to clarify, I mean, we can't start with like at the basics of group theory. We gotta start a little bit less like. I think like because I want to make sure.
Oh yeah, you're right.
It's like if we say it's a non-abelian group of order 8, people that haven't taken abstract algebra are gonna be like, all right, I'll click off the video.
So a set is just a collection of elements. It could be like a collection of elephants or like dinosaurs or numbers. That's what most sets are. And then a group is just a set with some special restrictions placed on it. So it has like 4 main restrictions. It has to be closed under whatever operation.
So
breaking that down.
Yeah, let's break that down a little bit too. Okay, so with numbers, like we have a lot of different operations that we use. So for example, we can add them together, we can multiply them, we can divide them, we can do all sorts of weird stuff to them, right? And so those are just called operations. And so basically when she's talking about like a set being closed, what that means is that when you define an operation on a set, so when you say, like for example, like let's have a set of numbers and let's define the operation to be addition, it means that we're adding all the numbers in the set together
and then
with an operator.
Yeah, any numbers that you add, any operations that you perform, the result of that operation, so on the other side of that equal sign, that number that results is also going to be a part of the group.
So I think here it might be helpful to have an example of like different sets that we're talking about and different operations and closure or the lack of closure under the operation. So for example, if we take the set of numbers just 1, 2, and 3, right, we can define the operation of addition just like we normally would define it, right? So we get 1 plus 2, right? And 1 plus 2 is 3, and 3 is in the set.
So that's all good.
So that operation is all good. But then if we take 2 and 3 and we add them together,
that'll give you 5, and that'll be out of the set. So that set wouldn't be closed under the way we defined addition to be just normal everyday addition.
But on the other hand, if we take a set of numbers like let's say the counting numbers, right? So the counting numbers are
natural numbers.
Yeah. So they start at 1 and they go all the way up through the biggest number that you could possibly imagine, right? So if we take any number, right, and we add it to another number, we're going to get a bigger number, but that number is still going to be in the set of all of our counting numbers.
Yeah.
So that's what we mean by closure.
It's a good example of just a normal closed group. So then in talking in terms of a set to a group, closure is an important element of being a group because it kind of lets us have this predictable, flow of what happens when we perform operations within the set.
Right, because what happens if we perform an operation and then the element that we end up with isn't in the group anymore?
Yeah.
That's like sort of behavior that's we haven't really defined, so it could be anything, it could be nothing. It's just we run into like weird issues when we try and do math with things that aren't well defined.
Yeah, exactly. So most of these properties are ensuring that the group is well defined, or that it's a well defined set in terms of a binary operation, or just an operation in general.
Okay, let's move on to the next.
Yeah, so we got closure. Next would be associativity. So this is probably something you learned about way back in elementary school and then promptly forgot, like I did.
Yep.
So this is basically, and we'll overlay an image of what exactly associativity means, but taking three elements in whatever set, let's just call them A, B, and C. They can be numbers like 1, 2, and 3. When you have parentheses around, let's say, 1 plus 2 and then plus 3, that should equal the same thing as if you had parentheses around the 2 plus 3 portion of that expression. So again, just kind of making sure that your operation is going to be predictable under whatever circumstances.
Yeah, so I think the important thing to remember here is like order of operations, right? So like way back in the day you learned PEMDAS.
Yeah.
The first thing you do is everything inside the parentheses. So basically what we're talking about when we're talking about commutativity,
Associativity.
Basically what we're talking about when we're talking about associativity is that no matter what way you do the operation that you've defined, the outcome is going to be the same.
Yeah.
So if you do 1 plus 2 first and then you add 3 to that, or if you do 2 plus 3 first and you add that result to 1, you're going to get 6 either way. And so that's just all that means.
Okay, cool. So yeah, I guess our next two group axioms are semi-related. So they're going to be having an identity and having an inverse. So we'll start off with identities. So identities are something that most people don't even think about, but they're just any element such that when you add it to any other element of the group, you're going, or add being our operation here, when you perform an operation with that element and any other element in the group, you're going to get out that same element that you performed it with. So in terms of like regular integers that you're probably used to working with, that identity element is going to be 0 with the operation of addition. If that makes sense.
Yeah, so I think in layman's terms, like 0 is the additive identity.
1 is going to be your multiplicative identity.
And it's just a number that when you add it, you get the same thing as you started with. So 5 plus 0 is still going to be 5.
Yeah.
So that's going to be the additive identity, and 5 times 1 is still going to be 5, so that's the multiplicative identity.
Yeah. Then kind of our last axiom is going to be having an inverse. So that does go along with identity because you can't have inverses without having a defined identity.
So let's talk about like what an inverse is.
So an inverse is going to be when you have an element of your group, you want to have the existence of another element in the group that when you perform an operation between the two elements, it'll get you out, it'll, I guess, spit out the identity of the group, whatever that is. So for example, in the integers, if we had a number like 5, and under addition, our inverse is going to be -5, because when you add 5 to -5, you're going to get out 0.
Yeah. So going back to the example that we used earlier of the natural numbers, the counting numbers, right? 1 through the biggest number that you can imagine. That wouldn't be defined as a group because it fails the proper, it fails having an identity, first of all. But it also doesn't have inverses, right? So if we assumed that 0 was in the group of natural numbers.
Yeah, if we extended the group to include 0, because you can include 0.
Yeah, you can.
Yeah.
So if we included 0 through the biggest number that you could possibly imagine, we'd run into the issue of, well, if you have 5, what do you add to it to get back to 0? And the answer is there's not a number in the group that's defined.
Exactly.
So that's an example of a set that fails a test and is not a group.
Yeah. So I would say that's a pretty that fails a test.
Fails a test.
Ooh. So yeah, now that we have those basic principles of what it means to be a group defined, then we can kind of talk about some special groups that have cool everyday applications and just general things that are worthy to talk about.
Okay. Wait. Okay.
I guess we can also
let's talk about abelian and order first.
Yeah, so groups, any group will also have other properties that are not common among all groups, but that are semi-specific to them, or certain properties that some groups have and others don't. So one of these properties is called if a group is abelian or not, and it essentially means the same thing as that operation on the group is commutative.
It's just a fancy word.
Yeah, it's just a fancy word for commutativity, pretty much.
So, like, going back to one of our examples with just, say, like addition over all integers, right?
Mm-hmm.
So that's like all whole numbers, or the counting numbers plus 0,
Yeah.
and their opposites, right? So if we add 1 plus 2, we're going to get 3. And then if we add 2 plus 1, we're also going to get 3, right? So that's an example of
A group that's commutative. Yeah.
right. But on the other hand, right, if we just, so now if we're just talking like fractions and all numbers, if we divide 4 by 2, we're going to get 2.
Mm-hmm.
But if we divide 2 by 4, we're going to get half.
Yeah, so that would not be it.
Because we've switched around the order of like the elements relative to the operation, we get different results. And so that's what we're talking about. We're talking about abelian and non-abelian groups. That's all that means.
Yeah. So that's a pretty simple topic. And then another, I guess, quantifying aspect of a group is that every group has an order, which essentially just means how many elements are there in this group. Order can be used in sets, right? Or is it only a group thing? I think it's a group thing.
No, I think it's a set thing too.
Okay, I mean, it's a pretty simple concept.
Because like the order of like, you know, when you have like power sets,
Yeah.
like you talk about order of the power set.
Okay.
If you take a set and you make a power set out of it, you're like, oh, what does the power set have order of? Because it's
The order of a group or a set is just going to be the number of elements in that set or group. So it's a pretty simple concept.
yeah, it's just a number of elements.
Yeah.
It's like some sets have infinite order.
Mm-hmm.
Some sets have finite order.
Yeah, so...
Easy day.
Yeah, a lot of the finite ordered sets are actually super interesting, surprisingly. I always thought it would be the opposite way around, you know?
So now that we've sort of like laid those foundations, I guess we could start introducing.
What exactly Quaternions are?
Yeah,
Okay.
I think we can do that, right?
Yeah, I think we can.
Okay.
So, Quaternions are a group. They have all of these axioms, and they're a group of order 8, meaning that there's 8 elements inside of this group. Now, those elements have kind of a very specially defined interaction with each other, but we can kind of simplify it down and kind of give a geometric interpretation of where they come from and like what exactly they mean, instead of just throwing a bunch of letters on a whiteboard and telling you that this is how they interact, because that's not super fun for anyone.
Yeah, I mean, I think math sort of works in like 2 ways. Sometimes we like the concepts of math exist independently of the physical phenomena that like well, I guess this is debatable, right?
Yeah.
But I think that the concepts of math exist independently of the phenomena that they define.
Mm-hmm.
In this case, though, Quaternions were actually created to model a specific
Geometric aspect of the world. Yeah, they weren't formulated to, solve equations or define something abstract. They were actually kind of almost invented to explain this phenomenon that goes on in our everyday lives, and that's just objects can rotate and 3D objects can spin around on multiple different axes, and people wanted to figure out, okay, how can we represent this mathematically with different variables and relationships between them?
Yes, I mean, I think it's really interesting in general to look at like how, like, sometimes we'll get, like, I'm trying to think. Like, probability is a really good example of a field that was created because of a practical need.
Yeah.
It's like people wanted to gamble, basically.
Mm-hmm. Yeah,
like
people
that's why the
like,
whole field was created.
Yeah.
Just like, hey, like, what are my odds of winning?
Mm-hmm.
So, if we want to take an example of like a mathematical concept that like has a practical application, but it wasn't originally created with that application in mind, like, we can talk about the group of order 2, right? Mm-hmm. Which is essentially like the binary representation of digits that our computers use to process information. So basically,
Yeah.
microprocessors, right, when data comes through, have an on or an off state. We can represent that with zeros and ones. And we can do like awesome things like build mathematical models, display graphics, play games, and all of that is just fueled by the zeros and ones that run through your processor, which like we understand because we understand how that group of order 2 works.
And it all boils down to this one singular group of order 2 that is so unique that any other group of order 2 is going to be isomorphic to it, which we don't have to get into, but basically that's like the only unique group of order 2 that's possible. And it wasn't, created in terms of computers, but down the line it just happened to be super useful. And yeah.
All right.
So where were we before that little interlude? Okay, so graphical representations of...
And geometric, rather, but yeah.
Yeah, geometric representations of groups. So way back when, in the 1800s, some Irish dude was really thinking hard about, hey, so like we kind of have some idea about 2D rotations via the complex numbers, but we had no idea how to do this in 3 dimensions, and that's how our world operates. So just taking a step back and kind of explaining how complex numbers play into rotations. So complex numbers can be represented with the classic a plus bi, where I squared equals -1. That's another rabbit hole. Complex numbers are crazy.
If you don't have a great understanding of complex numbers, I'd really encourage you to maybe go watch some content or read some content on how complex numbers work, and familiarize yourself with the complex
plane.
And familiarize yourself with the complex plane. Because that's going to be helpful, and I don't think we have enough time to go into all of that in this video.
Yeah, there's entire hour-long lectures about the complex plane, I'm sure.
Well, I imagine there's more than an hour.
Oh, yeah. Yeah, complex numbers are everywhere. But you've probably experienced them mildly in your high school math classes, and just when you're trying to find roots of equations that don't have real roots, that kind of thing. The complex numbers are also great to describe 2-dimensional rotations. So for example, if you have some point, let's say 1, 2, everyone really knows how to graph 1 point. That's just,
I wouldn't say everyone.
1, 2. But you can also use complex numbers to describe that point. In terms of the complex form a plus bi, that a and b can be written in terms of a coordinate pair.
Just like the Cartesian plane.
Exactly.
Where you have the double, so you have an x and a y coordinate, right? Complex numbers have a real part and an imaginary part, which can be represented as 2 different axes on a graph. So your x-axis that you think of traditionally is your real part, and what would traditionally be considered your y-axis is your imaginary part.
Yeah. So that's just kind of translating complex numbers into a graphical representation.
And then with regards to rotation.
Yeah. And then with regards to rotation, you can rotate that vector formed by the point connecting the origin to the complex point. That rotation can be formed by multiplying the complex number by a multiple of I. So if you multiplied, let's just say, our point 1, 2, going back to that point, that would be 1 plus 2i. If you wanted to rotate that 90 degrees to the left, then you would just multiply it by I. And then you can kind of perform some algebraic manipulation on that, and you can see that if you were to go through and FOIL it out and then graph that new point that resulted after simplifying I squared equals -1, then you would get that 90-degree rotation.
Nice.
Yeah.
So this guy Hamilton, there's a play about him. Great guy.
Different guy, but Irish mathematician Hamilton, way back in the 1800s.
Big potato guy.
Big potato guy.
He's like, what would happen if I took a potato and I flipped it upside down? How do I model that? I know how to model a potato.
Exactly.
In 3 dimensions, right? You do it with 2 parabolas.
Sphere parabola thing, yeah.
And then or paraboloids, I guess, right?
Yep.
And then you put them together, and that's how.
Yeah, we had a cool paraboloid exhibit at the math museum.
Okay, well.
So yeah, so this guy Hamilton was just walking over a bridge one day, and he was like,
He was walking under a bridge.
Was it under?
It was under.
I thought there was water under the bridge.
There's like a path underneath.
Okay.
There's like she doesn't know about bridges.
I don't know about bridges. It's okay. So he was somewhere in the vicinity of a bridge.
That's
it's
fair.
not really important to the story other than that. He was really thinking about how do we model 3D rotations? And then he just had this epiphany that we can model 2D rotations with complex numbers by adding this one I on. But in order to model 3D rotations, we need to add 2 more values similar to this I value. So he obviously called them J and K, because mathematicians are not super creative. And then the Quaternions were formed with these 3 kind of basis
so began
elements.
the Quaternions.
Exactly.
And that is the end of the story.
Yep. Have a nice day, ladies and gentlemen.
Good night and goodbye.
So now that we've kind of introduced it, I guess we can, and so now we know that there exists this group with, that can in general form just be written as some expression of A plus BI plus CJ plus DK. And that group can model these 3D rotations similar to how the complex numbers does in 2 dimensions. But it can't just be any I, J, K variables. These variables have a really special relationship with each other. They love each other very much.
Oh my.
Oh god.
Alright, so I guess before we define that, we should talk about like, so in space, like, okay, so in like 3D space, right, we can move stuff around. Like I can move. Okay, so in space, right, we can do 2 things, right? So we can translate something and we can rotate it.
Yeah, that's a good point.
So, with reference to the Quaternions, right, when we add Quaternions together, right, we're representing a translation from one point to another, right? So that would be, for example, if we're just sliding this water bottle on the table, that's a translation.
Yeah, that's translation. Yeah.
Right? And then we slide it back to its original position, right? So we have, this gets into the concept of having
inverses.
Additive inverses, which is one of, as you can maybe remember, one of the requirements for a group. The other thing we can do with this water bottle is throw it at people that are walking by because they're making too much noise.
Yeah, exactly. And that would be a rotation.
A translation and a rotation.
Yeah, for sure.
We'd have to translate out of here real quick.
Oh yeah, but we're not going to do that today.
No, but the other thing we can do, right, is just rotate the water bottle, right? So if we rotate it and lay it down on the table like this, we haven't really moved it anywhere, but we've, well...
It's more, yeah, it's like a shift.
Yeah, but we've rotated the water bottle, right?
Yeah.
And so the way that we represent that with a Quaternion group is by multiplying 2 different Quaternions together.
And that kind of brings in this whole other aspect of this second binary, the second operation to a group. So a group that has multiple operations kind of falls into a third or another category called a ring, which we don't have to get into too much, but it essentially just adds another dimensionality to a group, and it gives it this second operation that it can use to I don't know, change itself. And
basically,
yeah.
I mean, it's a way to oversimplify things. A ring is a group that has multiplication.
Yeah.
If we want to think of it like very traditionally, right?
Yeah.
Addition with a group, we add multiplication in. If we're all good with multiplication with some properties,
yeah,
we call it a ring.
So yeah, the Quaternions fall into this ring category because when you multiply them together, when you have that second binary operation, it allows you to rotate things and not just translate them from place to place.
Yeah. So in order to make all this stuff work, right, we need to, like, we can't just say, look, we're just gonna add them like regular numbers, right? Or multiply them like regular numbers, because A, we wouldn't know how to do that because there's now, we got letters.
Letters, yeah.
And B, they wouldn't represent the physical behavior that we're trying to model. So we need to put some constraints on the relationships between variables.
Yeah.
In order to make this Quaternion group useful to us.
And if we were just adding them together, we could almost just treat I, J, and K like you would any other variables when you're adding equations. You just would add their coefficients and then keep them as is, I would say.
Yeah.
So we don't even...
We have groups like that, right? Like Z2
Yeah.
is just a pair of, like...
I wouldn't exactly compare it to Z2.
No, but I'm saying, like... We have like Z2 is we add elements pairwise and we multiply them pairwise.
No, totally, yeah.
And that's like, so in this case, right, since we have...
Do you mean like Z cross Z? Well, same thing, but like...
Yeah.
Okay.
Yeah, exactly.
Yeah, you're thinking of them in terms of like coordinate pairs. Yeah, so it's almost like adding coordinate pairs, adding everything pairwise. And then if we're just adding elements of the quaternion group together, then their relationships, the relationships between I, J, and K are not... they don't really need to be defined, but once we add in that second layer, that multiplication layer, then we have to define, okay, what happens when we multiply I and J together, or I, J, and K together, and does order matter, and that kind of thing comes into play.
Yeah. So, what are the relationships that we need to define?
So
in terms of addition, right?
Yeah.
That's straightforward.
But in terms of multiplication, we can define these specific relationships, so we can just run through them real quick as they're defined and then kind of go into why it works and how it works in terms of the rotation. So the most basic, I guess, definition is that I squared equals -1, J squared equals -1, and K squared equals -1. But from that you would think, okay, I squared equals J squared equals K squared, but that's not the case, right?
No,
it's not the case.
It's not the case.
Yeah, I don't know why I sounded so unsure about that. Yeah, so just because all of their squares equal -1, the three of them are not all equal to each other, even though that's how most traditional math works. That's not how this works.
So in terms of relationships to each other, right, it's pretty easy. All we do is we say, well, I is going to equal JK. And then from there, start moving stuff around.
Yeah, so then we move, so if I equals
you move K over to the other side.
Yep, and then we get KI equals J, and then we can also get JK equals I, right? Is that how it works?
Yeah, it's the same thing as I equals JK.
Yeah, either way, we'll put up some we'll put up some visuals for you guys in the video that just kind of shows this relationship. It's not super meaningful since it's just kind of a jumble of letters, but we're going to make it meaningful by explaining why those letters, why the relationships work to represent our physical rotations.
So one of the techniques that I use, I actually invented this technique.
What is it called?
My last name is Kaylee. My last name is Digraph.
Alright.
Oh, what do you know? Physics, folks. When Becca pushes me, her chair moves.
One of the common techniques that a lot of mathematicians use to model group structures and how they interact are called Cayley diagraphs. So we learned all about these in abstract algebra, and they're a really fun way to visualize groups and just kind of see what happens when you add this element to this element and what kind of patterns exist within the group.
I think they're super confusing and I dislike them.
Digression by...
For what it's worth.
But,
so maybe don't use them.
But I don't know, I think they're pretty useful.
Maybe pretend they don't exist.
So,
that's what I did. And then when it was on the final, I was like, well, guess I'm not getting any of this section.
Nope. Actually, yeah, so one of our final questions in abstract algebra was to draw the Cayley diagraph of the Quaternions, so...
And compare it to the Cayley diagraph of D4.
Yeah, which is another group, so...
And they're both of order 8, and so the question was, how are they different?
Yeah, which they're not isomorphic to each other. But as you can see by this Cayley diagraph on the
screen... I knew that, I just didn't know to...
Yeah. So the Cayley diagraph on the screen that you guys are seeing is going to show the relationship between I, J, K, and then 1, which is going to be that identity element when they're multiplied with each other. And as well as all their inverses, so -I, -J, -K, and -1. Anyway, the green lines are going to represent multiplication by J, and the red lines are going to represent multiplication by I. So this whole group structure can just be defined by these two operations, I guess. And this just kind of shows some of the ways that they interact, and then we can kind of translate this in terms of the 3D rotations a little bit later on.
The Quaternions not abelian, right?
No.
Because you can't. It's not abelian for multiplication or addition.
I think it is for addition, but not multiplication. Right? Because for a ring, the addition has to be abelian, but the multiplication doesn't. But most of the time when you're dealing with Quaternions, you're dealing with the multiplication.
But what happens if you addition is translation, right?
Yeah.
So what happens if you translate something in a different order?
It's still the same.
It ends up in the same place.
If you rotate it in different.
Then it ends up in a completely different place.
Yeah.
And we know that from like diagonal groups.
Yeah. Yep.
Okay. Do you want to talk about these?
Yeah. Sure. So the next little graphic we're gonna show you guys on the screen to explain the Quaternions. I thought this was really cool when I saw it. I actually saw it for the first time today. But on top you can see the classic multiplication table for the Quaternions. So this is displaying the same relationship as you guys saw in the Cayley diagraph, just like the general relation as it's defined.
Just a different representation of the same thing.
Yeah, which is just helpful when you're performing operations between them. But these next two are new to me, and honestly they're really cool graphical representations. They kind of remind me of like heat maps for like other things that I do at work, but that's a digression and a half. But yeah, so this is kind of like representing the group in like a visual way that's interesting. And just as you can see in like a multiplication table for a group, let's look at the left one with all the colors. So you can see that there's one blue element, let's say the dark blue. There's one of each in every row and column. And we just talked about...
What does that mean, Becca?
That means that there's no zero divisors. Yeah, we learned that in class.
Pretty nifty.
Yeah, so these visual representations and even just the multiplication tables can kind of help us define and show certain qualities of the ring. So now we know that, okay, the Quaternions don't have any zero divisors. They're still not a field for other reasons, which a field is just kind of like a ring with some extra properties. But the fact that it doesn't have zero divisors is really helpful when you're performing some operations, and it helps kind of just I don't even know.
We can talk about that later with practical applications too, because it's one of the benefits of using Quaternions opposed to like Euler angles or something, right?
Yeah, so we'll come back to the whole no zero divisors thing, but basically all it means is that when you multiply any two elements together, you're never going to get the identity element back unless one of them is multiplied by the identity. Is that what it is, kind of?
Yep.
Yeah. Okay. But yeah, we'll get back to that later. I just thought these were really cool visuals to kind of show the relationships in a different way that wasn't just a bunch of letters on the screen.
Noise.
Yeah. So yeah, now we can move into some of our applications.
So now that we're like done with the boring part of the video, we can move on
my
to
favorite part, but okay.
Alright, in my case. And now that we're done with the boring part of the video, where Becca was talking.
Rude.
We can move on to the interesting part of the video where we talk about why Quaternions are useful, because why bother doing math if we can't do anything with it?
Pure math majors.
Pure math majors, click off now. It's about to get real nasty.
Yeah.
Alright,
So one of our favorite applications of the Quaternion groups is...
So one of the places that I've seen Quaternions before, actually the first place that I was introduced to Quaternions, and the only reason I knew vaguely what they were when they got brought up for the first time in abstract algebra, was that I had seen them when I was doing some iOS programming. Mm-hmm. And it was like, I was building this like really simple game that like people could like basically like fly like a little simulator.
Cool.
In order to control like the fake airplane, what I wanted to do was have people be able to tilt like their iPhone. Mm-hmm. Right? In order to do that, I need to know like what the position of the phone is.
Yeah.
And how it's changing over time, mm-hmm. in order to like control where the airplane is going.
Yeah.
So that was my first introduction to Quaternions. And they're like in every like graphics library, and then on like basically every phone, whether it's iOS or Android, you're gonna find like some sort of quaternion representation of motion. So in iOS, it's gonna be the core motion API, and the okay. So in iOS, it's going to be the core motion API and the scene kit API, which are both core motion has to do with device rotation, and scene kit has to do with graphics. It's just higher level than like Metal or OpenGL. If you know what either of those are, it's just higher level.
I don't. It's okay.
I guess if you know what OpenGL and Metal are, then you're going to know what core motion.
Yeah, you're going to know what quaternions are too.
Yeah, it's true. So basically, because quaternions are like, I think a lot of people think they're like super scary and unapproachable because they don't make a lot of sense to people.
No.
It's like, why when I like multiply these things together do I get something that's completely different?
Yeah.
And I think if you don't understand the relationships that are defined for them, it can be like daunting. And I remember like when I first saw them, I was like, what in the heck is this? Like, I'm a math major and I have no idea what this is.
Yeah.
So the other option that you get is you can represent motion with Euler angles. So basically, those are sort of the traditional angles that we think of.
Yeah.
So that would be pitch, roll, and yaw.
And is
like
that
the three-dimensional?
Those are represented using like matrices usually, right? Or they can be.
They can be.
Okay.
Yeah. I mean, you can like also just pull them out of the API.
Oh, okay. Yeah.
That's.
I always think about like rotations and translations and stuff in terms of like matrix operations.
I think the quaternions are represented with matrix like stuff. And the linears they usually do, so you pull out like pitch, roll, and yaw.
Okay.
Anyways, if you're not familiar with what pitch, roll, and yaw are, maybe go look it up. I don't want to explain it.
No, yeah, we don't have to. We're here for the quaternions, not for the other shit.
But there's a couple of reasons why quaternions are going to be more useful, or they're going to be at least preferred over using Euler angles. First of which being, usually it's like a more compact representation of motion, and so computations on these objects can be conducted more efficiently when you're using quaternions as opposed to Euler angles. The other thing is that with Euler angles, you have to worry about something called gimbal lock, and with quaternions you don't. So this actually comes back to the no zero divisor thing, right? So when I add like any two, or when I multiply rather, any two quaternions together, I know I'm not going to get zero unless one of them is zero.
Yeah.
Right? With Euler groups, you can get some weird behavior sometimes. And basically what ends up happening is that two axes are parallel to each other. And so you lose a degree of freedom in your representation.
Yeah.
And this is something that you'll, like, if you ever read up on flying, traditional gimbals are basically these devices that like spin so that they're stable in the air, and they're used for all sorts of stuff in airplanes. Like you would use them for your attitude indicator to tell if the airplane's going up or down or it's like rolling at all. You'd also use it for like your direction. So as opposed to using a compass, you use this other device that you set to a compass, and then it has a gyro inside of it, or a gimbal inside of it, I guess. It's a gyro, but whatever.
You're right.
So anyways, with your gimbals though, if you line up two axes to be parallel, you'll get gimbal lock, and you lose like a degree of freedom. And that's what happened on like, the Challenger, I think.
I have no idea. What?
Yeah, one of them got gimbal lock. They fixed it.
So, is there any prospects for quaternions to like be implemented in sets that doesn't happen, or is that going to be impossible in that scenario? Because
so in terms of like gimbal lock,
it's like a physical phenomenon.
It's a physical phenomenon that has to do with like just the rotations of objects, of physical objects. So it would be interesting to see like a physical system that more approximated Quaternions.
Yeah.
But I don't
know if it's possible.
I don't. Yeah, I have a hard time visualizing that, right? But,
yeah. I have a cool idea to like knock around to see if you can come up with anything.
Yeah, beats me.
Yeah.
But anyway, so those are two of my favorite applications. I love the computer graphics stuff and the motion stuff on phones. And then they also, I mean, you know, I'm sure that if you go look on like flight software, you'll find Quaternions everywhere. Because for something that needs to be computationally robust,
oh yeah,
you're not going to want to use something that can fall into a state where, okay, now I've lined up two axes, I'm getting 0 out, so whatever additional operation I add to that is still going to result in 0, right? And that means you have to reboot the whole system.
Yeah.
So obviously Quaternions are going to be preferred.
No, that's really cool actually. Like the whole fact of 0 divisors, which seem kind of very theoretical, and most of the time they come up in like modular arithmetic kind of situations. It's really interesting to see them like play into a physical phenomenon and cause issues in flight systems and that kind of thing. Or they would cause issues if they existed and Quaternions weren't used.
Yeah. Thanks for coming.